Hello, everyone, and thank you for joining us today. My name is Sean Sullivan, and I will be your host for this Technology Gateway webinar on traffic-aware strategic aircrew requests, better known as TASAR. Our presenter today is TASAR project lead David Wing. David is a principal researcher in the Crew Systems and Aviation Operations branch of NASA Langley Research Center. He holds a bachelor's degree in mechanical engineering and a master's degree in aeronautical engineering. David's career spans nearly 30 years of research in air traffic management and propulsion aerodynamics. His current research focuses on airborne trajectory management, where he develops advanced cockpit-based automation technologies and applies them across a roadmap of aerospace applications, from current day flight path optimization to advanced future concepts of airborne operational autonomy. In 2016, David was awarded the NASA Exceptional Technology Achievement Medal, and the TASAR software was named NASA's Software of the Year. Now, following David's presentation on TASAR, Jennifer Viudez, a licensing specialist at Langley Research Center, will be giving a short presentation on how NASA licenses technology like TASAR to outside organizations. But before we get started, let's do a couple of housecleaning items. I'd like to point out that your microphones will be muted throughout this presentation, so if you have any questions, please type them into the chat box, and we will answer them during the Q&A session at the end. So at this point, I'm going to turn it over to you, David.
Okay, Sean, thank you very much. Hi, folks. It's great to be talking with you today. My subject is TASAR, Traffic-Aware Strategic Aircrew Requests. And it's a NASA flight deck software application for en route flight optimization. You can see a photo of the software here displayed on the electronic flight bag. This is what's in our flight test aircraft, which I'll talk a little bit more about. We tested this a couple times in flight. And you can see the TAP software, Traffic Aware Planner, which is our software application, on the iPad here as an electronic flight bag. And so this is the software application that enables the concept of TASAR. The TASAR is, like I said, a rerouting application. The operating environment is for the en route phase of flight. And the en route phase of flight is very dynamic. You have aircraft that have filed a flight plan, and that was based on the current winds and weather forecast. It could be several hours old by the time the flight plan is filed, and they use that information. By the time the aircraft is in the air, the winds and the weather may have changed from the forecast. It may not have developed quite the way it was originally planned or forecast to develop. And you have other factors in the airspace that affect the route of flight as well. So, for instance, special use airspace. Restricted airspace goes hot and cold throughout the day typically, and can make airspace available or not available during that time, and that can be dynamic. And so as the aircraft is flying here, and again, the original route of flight was, shown here in magenta, was planned perhaps many hours ago. There are opportunities for pilots to request of an air traffic controller a change to the route to improve the flight in some way. And they would typically do this today through a voice request. So this is the operating environment. The issue being that pilots today don't have tools that can help them determine the best reroute to request to optimize their flight. So they will tend to use rules of thumb and experience to make requests. For instance, it could be very common for pilots just to ask for a direct to a downstream waypoint, assuming that would be a shortcut and would save time. Whether it does or not may depend on the winds, and they may not have that information in front of them. Same thing with altitude changes. It's typically thought that climbing to a higher altitude is more fuel efficient. And again, that really depends on the winds and the weather, the airspace environment. So the opportunity here is to provide technology to support the pilot in determining during the flight what would be a more optimal route based on some metric that the pilot or the aircraft operator would use for optimization. What would be a route change and or an altitude change that would achieve their objectives for optimizing the flight, but also would be approvable by the air traffic controller. And so another factor in the airspace that gets taken into account is the traffic. And in fact, it's in the name of TASAR, Traffic Aware Strategic Aircrew Requests, indicates an important role for having traffic surveillance because that's one of the most important things that the air traffic controller is going to be looking for in a reroute request. Does that traffic create a conflict with the request? So a part of the operating environment here is also connectivity via airborne internet data services. And this provides the opportunity to get real-time updates to all types of relevant information to aircraft operations and to flight efficiency. So, bringing on board the latest winds and weather, for example. So that's the operating environment for TASAR. TASAR basically is depicted in this graphic is an application, software application, and a capability that pilots would have, and it would be installed right in the aircraft. We've targeted the electronic flight bag as a place to host this software. And it is leveraging not only the onboard computing power of EFBs, but also connectivity to real-time data. So connectivity onboard the aircraft would include the EFB connected through an aircraft interface device to the data buses of the flight management system or other equipment on board. And that would provide this software with access to the aircraft's current state and the current route of flight, current active route in the flight management system. So it's always up to date with what the aircraft is programmed to fly. It can also connect to other aircraft sensors on board. For example, their onboard weather radar is an opportunity to bring in the weather picture that the pilots are looking at and feed that into the tool as well. So that's the capability that we're looking at. So that's connectivity inside the aircraft, having up-to-date information about the aircraft's current state and its route of flight and other information. Then with external data links, we have the opportunity to connect the same software to data sources outside of the aircraft, from the ground or nearby traffic aircraft. So ground connectivity, through an airborne internet or other type of data link, provides access to the latest wind forecasts and wind models. So as those are updated by the weather service provider, that latest up-to-date information can be provided right into the tool here, our real-time trajectory optimizer. Same thing with weather data, ground-sourced weather, convective weather data, or other types such as turbulence. That kind of information can be collected, turned into polygons, and sent into the software, in near real time. Airspace status, so restricted airspace as it goes hot and cold. That information can be updated in real time, provided to the software. And as I mentioned, the traffic data. This project has been focusing on ADS-B, Automatic Dependent Surveillance Broadcast, as a source of traffic data. So if your aircraft is equipped with ADS-B in, this software is capable of reading that information in and taking that into account in the real-time trajectory optimizing process. So lots of connectivity to data. And what we're going to do is to take that to the next level of supporting the stakeholders of an aircraft's trajectory, which would be the pilots. So as I mentioned, pilots making request to air traffic control. We're going to help them be better informed about the type of reroute that they would request in terms of their lateral path and their altitude. If you're an airline, you have a dispatcher who is also following the flight and is a stakeholder in the trajectory of that aircraft and is typically involved in significant reroutes of the aircraft. So we will be supporting that interaction between the pilot and the dispatcher as well. And then air traffic control ultimately is the approver of trajectory changes in flight. And so we seek to increase the likelihood that they would approve a reroute request by taking into account a lot of this information that's shown on the left side of the diagram. Now, of course, there are many factors that air traffic control take into account in managing aircraft and managing their airspace. And We can't possibly know all of that, but adding some of the key things here should help increase the likelihood of ATC approval of these reroutes. And then ultimately, the goal is to take your original route, which may be, again, based on old information when it was flight planned, not based on current up-to-date location of weather and the winds, so on, and to, during the flight, compute an update to that route, make a request to air traffic control, get it approved, and be able to start flying it. And getting to that stage is where the business case closes, so to speak. That's where the benefits start to accrue to the operator for having all this connectivity and the computing power and the software to turn that into an optimized flight. So that's the gist of TASAR. It's leveraging top-hat automation and connectivity both on and off the aircraft for airborne rerouting. So this project is about 5 or 6 years old. We started it back in about 2012. One of the first things that we did in the project was to conduct a preliminary benefits estimate to determine whether a technology like this, would produce benefits to users and about how much that might be. So we did some fast time modeling using a tool called FACET, NASA tool, for simulating future airspace concepts. And we basically took a period of flights in 2012 and replicated them in this fast time environment. And we chose a variety of flights, different city pairs, different stage lengths, different types of aircraft, and basically representing different operator types, just to kind of canvas the range of users to see where the benefits might be. And as these flights, these are historical flights, as they flew through in our simulation, we had algorithms that represented the TASAR concept, looking at many alternatives to improving that route of flight, and it was evaluated periodically as the aircraft went through the scenarios. And we applied some conservative measures, which would represent operating rules for a concept like this. No request during the initial climb to keep the focus above 10,000 feet. No requests with conflicts. That's the traffic aware portion of that. One request per sector, which would be, again, a typical operating rule of thumb for pilots and controllers. No request near the handoff, and no request close to the destination. So these types of things were applied to sort of filter out potential solutions. And we wanted to see, given all that, what kind of savings might be possible. So we ran this sort of 3 different ways. One with the optimization set up to look for flight time savings, another to look at specifically fuel burn savings, and then a third that would represent a weighted time and fuel objective, similar to the cost index and how airlines use cost index to represent the cost of time versus the cost of fuel, just to look at how that might balance out. So here are some results that we had found in this initial study. You can see we looked at this for several different types of class of airspace user, from network carriers down to business aviation. And we looked at the three different optimization objectives: saving flight time, saving fuel, and a balance of saving time and fuel. And you can see the types of savings that are there, 1 to 4 minutes or so of flight time savings on average per flight, or about 60 to 500 or so pounds of fuel, again, average savings per flight. And those are types of estimates that we generated. The next thing that we did is we expanded this study to look at sort of an annualized estimate for a couple of representative airlines. We chose Virgin America and Alaska Airlines. And this graphic shows sort of the results of that annualized benefit estimate. So this was assuming that, this is for Alaska Airlines, assuming that they equipped 109 737s. And again, given the cost of fuel at the time, and just these results were were developed, so this analysis was done using publicly available information about the airline's operations. So, the city pairs they fly to, the flight frequencies, aircraft types, and at the time what the the cost of fuel was, cost of operations. Came up with an estimate of about $5 million annual benefit for the airline, or about 2.89 minutes per flight, 27.8 gallons per flight on averaged across all the flights that were operating. So this kind of gives an idea of the size of benefit for an airline operation. In the graphic here, the thickness of the lines represents the size of the benefit for a given city pair. So the transcons tend to have better benefits, which makes sense because the longer the flight, the more opportunities there are to identify and achieve reroutes that would improve the efficiency of the flight. So that's look at the estimated benefits. Both those reports are published and available. So in this project, we prototyped the software that would support the pilot on board the electronic flight bag software application. We call it TAP, or the Traffic Aware Planner. As was mentioned earlier, it was highlighted as the NASA Software of the Year in 2016. And there were a number of attributes which are shown here that contribute to how the software is unique and innovative in its capabilities. And I'm going to give you a demonstration of the software here in just a little bit. I just wanted to highlight that this type of tool is unique in a number of respects, and among those are that it is performing route optimization right there in the cockpit for the pilot's use. There are other rerouting applications that are on the ground and would send information up. So this is on board. It is looking at optimization not only in the lateral dimension, but also in the vertical dimension and a independent combination of lateral and vertical. And also wanted to point out that it's flexible enough that it can be set up to optimize on different objectives and actually have the pilot change that objective in real time during the flight. And I'll show you that in the demonstration coming up here soon. So anyway, the TAP software is based on NASA's research and investments that go back over 15 years, going back to our research on operational autonomy. So there's a lot of heritage behind the algorithms here, and a lot of testing and refinement, maturity. As those algorithms were really designed for a safety-critical purpose of operational autonomy and separation from traffic and weather. The application here, of course, is non-safety critical. This is advisory only, but just to point out that the underlying software has a long and rich history. So let me tell you a little bit about the software, just a quick peek under the hood. The TAP software, the sort of the core algorithms, we call it the pattern-based genetic algorithm, or the PBGA. So this is the algorithm that essentially is searching the airspace in front of the aircraft, between the aircraft and its destination, looking for route optimization opportunities. And it is based on a genetic algorithm, so it is looking at sort of a directed random search approach. It is generating many hundred viable candidate reroutes that go through a process of evolution and competition through generations of routes. And I'll be able to show you an example of that here in a minute. It's essentially applying the principle of survival of the fittest. It's looking at each of those route candidates and determining which ones are the most flyable, optimal based on some metric of optimization, and free of conflict from the various constraints in the airspace. And this process is updated cyclically every 60 seconds. So every 60 seconds, it kind of takes a new snapshot of the airspace and does a new fresh search for solutions. The PBGA algorithm is supported also by a TAP trajectory generator, and a TAP conflict detector. All this was NASA developed software for this purpose. So looking at the inputs to these components, we have inputs from the aircraft avionics that give us the current state of the aircraft and the active routes. We know where it is and where it's headed. We have an atmospheric model that gives us a 3D gridded model of the airspace of the atmosphere in terms of pressure, temperature, and winds. That information is updated regularly from, in our case, we connect to NOAA directly and get the latest published wind and basically atmosphere model for the 3D airspace of the CONUS, of the Coterminous US. And then we also have an aircraft performance model on board, which is used again by the trajectory generator to model the current aircraft trajectory and each of these candidate reroutes. Then we have the conflict detector, which is fed information through external connectivity sources where we are bringing in traffic data through ADS-B in. This is the state vector data that's broadcast, and more aircraft are going to be broadcasting it here over the next few years as the mandate comes to fruition. And so we're receiving basically the state vector of these aircraft and using that to determine whether any of these reroutes are potentially in conflict with aircraft, and we would avoid that. Special use airspace. The restricted airspace in the U.S. is published, so we have that in a database, but we connect to the FAA website to get real-time updates to the status, the activation status of those airspace regions. And then convective weather polygons, and this can come from any source of any weather data provider, and it's really an opportunity for weather data providers to produce products that can support an application like this. We are connecting right now through WSI to get our weather data, and we have polygons that come from that data. And those all feed into the conflict detector. And then lastly, we have our optimization goals and user constraints. So this is the pilot or the operator telling the tool what it wants to accomplish or should be trying to accomplish. Are we optimizing on fuel or on time or the overall combination of time and fuel to reduce the cost of the trip? Are there any user constraints that need to be taken into account? And there's the TAP display is an interface to update those things in real time. The output of TAP is going to be reroutes that use the published name waypoints that pilots and controllers use for communication. So it's those published waypoint names. We have a database of that, and that would be updated on board on a regular basis. So this all flows into the PBJA, and out comes the optimized conflict-free solutions, and also the estimates of effect on time and fuel. If you were to request this route change, how much flight time or fuel would it save or potentially cost? The user interface is been designed using human factors principles and evaluated over multiple high-fidelity simulation experiments and flight tests. It's been very highly rated by airline pilots, and this is how they would interact with the tool. Just a few notes here on the some special qualities of the optimization engine. It is a pattern-based genetic algorithm, so it's using patterns of routes and route changes that are familiar to pilots and to controllers. So they look at these routes that come out of the tool, and they make operational sense. So this includes directs to downstream waypoints, and one waypoint, two waypoint off route back to a direct, a step altitude change, and a combination of lateral and vertical of the above two. I mentioned it's a genetic algorithm, so it's doing a random, directed random search, but it also includes exhaustive searching as well, because we don't want to inadvertently miss the more obvious solutions of direct to downstream waypoints or climb or descent to different altitudes. So that's mixed in directly into the algorithm, so they're all competing together. And also, each of these candidate solutions are checked against viability criteria to ensure that the turn angles aren't too steep and that the leg lengths are not too short. So essentially, they need to be flyable, and loadable into a flight management system. So that's all done and in a very highly efficient fashion. We've done a lot of work to make the algorithm compute very quickly. On a typical desktop processor, it just runs in a few seconds, and it presents the top-ranked solution of the lateral, vertical, and combo solutions to the pilot, again, on a regular basis. I've got a little video here that can show the algorithm kind of in work, in progress. The picture here on the right, the aircraft position is at the bottom center of the screen, and there is a black line which represents the current route of the aircraft. And so this would be your reroute, your original, maybe original filed flight plan, or your current route that was based on information that that is maybe a bit dated. You can see that it is circumnavigating some restricted airspace. There's also the red polygons there represent convective weather, and so that would be information that is could be updated on board from the onboard weather radar or from ground weather sources. There's also a wind field not depicted in this graphic, and there's traffic in the location, in the vicinity of our aircraft. There's other airplanes that are broadcasting ADS-B, and we're receiving that information. So what you're going to see here is, I'm just going to kick this thing off, and it's going to run through the 20 generations, each generation having 20 candidate reroutes. And every couple of seconds here, you're going to see it, let's go back one. Every couple of seconds, you're going to see it go to the next generation. And you'll see different colored routes. So the green routes are candidate reroutes that are conflict-free. The red ones have some sort of conflict with either traffic or weather or restricted airspace. Each generation, the best of that generation is shown in blue. And if you watch that blue route, you're going to see over the course of these 20 generations that it's sort of converging down to a common solution. This is the survival of the fittest, the convergence through the genetic algorithm process. But you also saw other routes being randomly generated to make sure that we're not missing something in the airspace there. Ultimately, it lands on this blue route. This is determined through that run to be the most fuel efficient, conflict-free route change that conforms to published waypoints and that remains clear of known traffic and weather and restricted airspace. So this will be presented to the pilot for them to make a request. I wanted to give you a demonstration of the software. This is the user interface. What I'm going to do is switch over to a running version of the software. I'm going to bring that up here and then bring it over to the screen so you can see. So this is the TAP user interface, and you're looking at the startup checklist. So when you launch the software, when a pilot launches the software, either at the gate on the ground or in the air, they need to go through and verify or enter some information to allow the software to go into its operate status. So I'm going to kind of go through this fairly quickly, but just to give you an idea, the current version of the TAP software, the pilot basically is just touching this. This would be shown on the electronic flight bag, and they would touch it with their finger going through this checklist to just verify or enter information as needed. At this stage, TAP is already connected to the onboard avionics data buses and has passed all those tests, and this is just indicating to the pilot that it has passed. The aircraft performance model in this example here at Boeing 777, so the pilot would just confirm that they're using the correct aircraft performance model for the airplane that they're on board. The navigation database, as I mentioned, we use data derived from the ARINC 424 database. It has the published waypoint names. It has other information that we use. The pilot would make sure that they are using a non-expired version of that. This, of course, is very expired, but I'm giving a demo, so I think that's okay. The destination. So there is some information that is not actually available over the AirInc data buses, even when you're connected to the flight management system. So some information has to be entered in. And this may be different from, depending on what aircraft type you're installed on and what avionics they have. In this case, we're flying to Denver, so I'm just going to enter that in. Another thing that TAP does, of course, is it reads the active route from the flight management system, but the data that comes over is in latitude, longitude coordinates, not in the form of named waypoints. So one function TAP has is to derive, or basically guess the waypoint name associated with a latitude, longitude coordinate. So the pilot would just need to go through and confirm that these match the route information in the flight management system. And they can just do that here one at a time. And if one of the names ends up being guessed wrong, they can go click this other button here, and these are other nearby waypoint names. They could choose that, or even enter in one from the keyboard. Or we can just go ahead and verify all and get done with that. The maximum optimization waypoint. So this is the last waypoint on your route that you would ever want TAP to optimize to. So you could go all the way to the destination, or you could pick a waypoint that might be the beginning of the standard arrival route. And this just cuts back on some of the solutions that TAP would be providing. The cost index, this is something airlines use to enter in the cost of time versus cost of fuel for the airline for that day, for that flight. Flight management systems, so you enter this into the flight management system. We also use it here in TAP. So you can put in even a very specific number. If this was calculated by some advanced cost indexing software, we can use that. And then the cruise speed, another piece of valuable information that is not available always on the AirInc data bus. If you're going to be flying an econ, you can use the econ speed, which uses cost index to compute. Or if you happen to know you're going to be flying a Mach 0.76, for example, you can enter that in. And this is what TAP will use in doing its 4D trajectory predictions. And then the cruise altitude. TAP starts working as you climb over above 10,000 feet, but it doesn't know how high you're going to be climbing to, so you can put in your cruise altitude. So we're done with our checklist. This basically says you can update any of those settings I just did on this other page. We're just going to go straight into our operate mode, and you can see TAP running here. I'm just going to range out a little bit. The position of the aircraft is down here at the bottom center. We see the magenta line is the current FMS route, and then we see this dash blue line, which is TAP's current recommendation for a reroute. I'll come back to this screen in a minute and show you a little bit more information. Let me just go over here to the upper left. These are our solution buttons. There's three of them. There's lateral, vertical, and combo. And so these are those three types of solutions that TAP independently computes. So the best lateral reroute without changing our altitude is currently being previewed over on the route on the map. And it shows the route change, which is to fly direct to Creep intersection. That's pretty funny. And then to Bylaw, rejoining the active route at Bylaw. And it tells you how much time and fuel, or fuel and time here would be saved by that maneuver. You notice that it just updated. This thing updates once a minute with the latest information, so it has done that. You have your vertical. This is recommending a climb to flight level 360. We're currently at flight level 300, so it's saying that you'll have a more fuel-efficient flight at that higher altitude, but you will lose some time in the process. Or a combo solution is a combination of a altitude and a lateral change. As I mentioned, you can actually change the objective in real time. So trip cost is using the cost index to balance time and fuel. I could change this to fuel, and it's going to recompute the most fuel-efficient solutions and display them to the crew. And you can see sometimes you'll come up with something that's very different looking. Let me put up here some of these layers so you can see the winds, special use airspace, and then we have several different sources of weather data flowing into here. And you can see The weather polygons are shown here. It's very difficult to see this. This dashed box is a SIGMET. You have restricted airspace or special use airspace. We don't show the traffic data because by showing traffic on the display, we would then be a cockpit display of traffic information, which has its own certification costs associated with it. So we're really just flowing the data of traffic data into the algorithm. So that's an example of what we call the auto mode. There's also a manual mode, which allows the pilot to enter in a route change of their own device or of maybe something that's provided to them from a dispatcher, or even air traffic control sometimes offers up shortcuts, and this would give the chance to the pilot to evaluate that pretty quickly. And so I'll just show you how this works. We can click on rejoin here, and I can either pick something from the list, or I can actually just touch right on the screen. When I touch on the screen here, it chooses the nearest waypoint bylaw, and it immediately does a trajectory prediction to our destination from present position to bylaw and on the rest of the route unchanged. It does detect that there are potential conflicts here with weather, even tells the pilot about how far away that is. What we can do is we can add in an off-route waypoint. I click on waypoint, and then I'll just touch anywhere here on the map, and it finds the nearest published named waypoint to wherever I touch on the map. You can kind of see it updating here as I go. And so if I were to choose this one, it's doing a trajectory prediction. It still sees the problem with the weather. So I can arrange to just miss that. I can even put in a flight level change. So let's put in that climb to 360. And lo and behold, it's actually detected a traffic conflict. So this is the traffic aware part of TASAR and the TAP software. It's looking at an immediate climb to flight level 360 and a direct to CAMS and back to bylaw. And over ADSB, it's receiving state vector information from an aircraft that is crossing roughly from left to right at flight level 340. We don't see exactly where it is because we're not showing the traffic information directly, just enough information to show what the problem is here. So the pilot would probably not want to make this request to air traffic control because they're likely to get turned down due to that traffic. So they could pick perhaps a different altitude. Let's try 320, and sure enough, that shows clear of traffic, and we could make that request. Point out one other thing here. There's this symbol that looks like a telephone in the shape of a D. That is our dispatch coordination icon. Many airlines have a criteria that if the reroute is large enough, they need to coordinate, the pilot needs to coordinate with dispatcher. And so we're computing that criteria and displaying to the pilot that this particular reroute is large enough to require dispatch coordination. We have a dispatch button down here where the pilot can record the results of that coordination, or in a air-ground integrated version of this, we could automate this so that it would be actually filled in by the dispatcher. Once that has been recorded, then the pilot could make the request to ATC, and they either would get it approved, and they could record whether that was approved as requested, or maybe it was amended by the controller. Or if it was denied, they could record what the problem was if it was specified, and that supports us with data analysis and determine what went wrong and what information would have helped that be approved. All right, so that's kind of a quick demo of the TAP software. Let me go back to the presentation and wrap this up. So let me talk a little bit about the maturity of the software. So we started the project back in 2012. The software itself goes back to more than a decade before that, actually, in our autonomy research. So the algorithms have been very heavily stress tested and evaluated in simulation. In 2012, we sort of repackaged this into the TAP software, to an EFB application. And we've run two human-in-the-loop simulations, high-fidelity simulations, looking at the human factors aspects of this application. What does it do to pilot workload, and is it a potential distractor to pilots, and things of that nature, the usability of the interface. We also did two flight tests conducted by our subcontractor advanced aerospace solutions in their Piaggio Avanti flight test aircraft. You can see the photo there. So once in 2013 and then 2015, we tested this in IFR in a certified aircraft environment, so it was not experimental. So, proper IFR flights in the airspace up and down the east coast. Our first flight actually went up north from the Hampton Roads area where we're based here at Langley, up into Washington Center and New York Center, and actually into Boston Center back. The second flight test went on the routes depicted here down to Atlanta Center, Jacksonville, testing out different aspects of the software. We did use TAP to generate and make requests to air traffic control, and we had good success there. We also looked at how TAP would interact with different constraints in the ATC system, and particularly here on the second flight test, we actually had researchers at the Atlanta and Jacksonville centers sitting next to the controllers that were working our flight, and then interviewing them after the fact about airborne user requests and what would constitute a more approvable versus less approvable request. So we learned a lot there. We invited pilots, airline pilots, and other senior pilots to come on board, test the software, and it was also tested on airline hardware. So over this project, our goal's always been to try to achieve tech transfer. We've done a number of things to try to position the technology for as much success in that objective as possible. I wanted to run down a few of those for you. We have, so early adopters is kind of what we're looking for, right? And early adopters need to build a business case. We provided, our benefits estimates to the operators to try to help with some actual numbers, and that information has actually been used by our airline partners to build business case to test the software. We know that early adopters want to leverage investments they've already made and industry trends. We've got the electronic flight bag and connected aviation, aircraft connectivity, both very significant trends and investments that operators are making. And so we've really designed right for that environment. And as a result, we've had leaders in those revolutions actually reaching out to us about this technology. Early adopters also want to avoid being the first to go for FAA approval. And we understand that. So what we did is early in the project did an extensive analysis of the FAA policies for EFB applications of this type and to see whether, what the approval requirements would be. And then we actually took that analysis up to FAA in DC and presented it to the actual policy writers, who gave us a green light for this application, saying that it's a perfect example of a Type B application for EFBs, or Class 2 EFB, what they used to call, and that all the policies are in place for an operator to move forward with requesting approval for it right away. Early adopters also want technology based on solid R&D. As I mentioned, this technology goes back well over a decade, and we also have done a lot of rigorous testing for usability in its current form in our simulations and flight tests, and it was very highly rated. And then lastly, we know that early adopters want to see new technology working in the real world, so that's why we did our flight testing in very busy, complex airspace. And we invited decision makers from airlines and industry to come out and evaluate it for themselves. And as a result, we are actually conducting now operational trials with a partner airline in revenue service, and starting to see TASAR mentioned in many briefings and showing up on roadmaps around the industry. So our partner is Alaska Airlines, and we're very excited to be conducting operational trials with Alaska. We have 3 aircraft equipped. These are 737-900 ERs, which they primarily use for transcons. This is going to be conducted in revenue service operations. We already have these aircraft equipped, and they are flying with the TAP software. And we expect the pilots to start using the tool in the next few months, and the trials will continue through 2020. And so along with Alaska Airlines, we're really pleased to have industry contributors participating in these trials. We have UTC Aerospace Systems, which is providing the aircraft interface device and access to the aircraft avionics data, also hosting our software. We have GoGo in-flight internet, which is providing also hardware that's hosting our software and, of course, providing connectivity to the airborne internet. And ACSS is providing the ADS-B in for the traffic-aware portion of the technology. All these companies are great to work with, and they are making valuable contributions all the time to this project between NASA and Alaska Airlines. Brings me to my last slide. I just wanted to talk a little bit about the broad opportunities that TASAR brings to the industry, and the opportunity it would provide to anyone who decides to commercialize the software. It is applicable to a diverse set of airspace users. I think you saw that in some of my earlier slides on benefits. A lot of my examples here have been airline-based, and that's because we are testing this in partnership with an airline. But our flight test aircraft was a general aviation aircraft and a corporate aircraft. Also, it would be applicable to military as well. It's also adaptable to a diverse set of optimization objectives. I mentioned earlier that TAP is capable of optimizing to save flight time, to reduce fuel burn, or a weighted combination, which results in overall trip cost reductions. There are other areas that TAP can be enhanced moving forward, bringing in turbulence data to improve and optimize the ride quality, taking into account other things like crew legality or overflight fees, or potentially even very complex multi-objective optimization that can vary on a per-flight basis. There's also the opportunity to expand to a diverse set of use cases. Some of these I've mentioned, immediately re-optimizing with winds aloft updates, proactively rerouting as the weather dissipates perhaps faster than forecast, or maybe it was just not properly forecast to begin with, and basically not waiting to get a better route, but asking for one. Areas for expansion could include including 4D objectives, so time of arrival constraints to the trajectory, and optimally meeting those. And that could come from ATC metering, flow metering, or it could come from company time constraints. And also there's a great opportunity for using datacom to, instead of using voice requests, but to adapt TAP to export routes into the datacom system. And then lastly, I just wanted to highlight the many opportunities for technology advancement and operational advancement using technology like this. This is basically a real-time trajectory engine and trajectory optimizer on board the aircraft. It obviously provides a tangible incentive for operators to connect up their airplanes with connected aviation and connecting to onboard systems. There's a great opportunity to integrate with existing technology on board, the flight management computer, data communications, onboard weather radar, other things like that. And then just moving forward to safety critical applications as the technology is enhanced and is hardened, and moving towards increased operational autonomy, which is again where we started with our research in the last decade. So that's my I guess my summary of the TASAR concept, and I appreciate your patience and attendance, allowing me to talk about this exciting technology developed by NASA.
All right, thank you, David. So we have received a number of questions so far on your presentation, and we will get to those very shortly. But as David mentioned before, one of the objectives here is technology transfer. So now one of my colleagues from the Technology Transfer Office here at NASA Langley is going to give a brief overview on how businesses can partner with NASA through technology licensing.
Okay. Thank you. Thank you, Sean, and thank you, David. My name is Jennifer Viudez, and I'm here in the Tech Transfer Office at NASA Langley Research Center. And hopefully you've seen something today that has sparked your interest about our technology and maybe some exciting ideas have been generated. So I want to change gears from the actual technical part of the presentation and talk a little bit about the business side and how you can possibly get this technology in your hands. This is a little bit of an eyeball slide, as they say, and the purpose of this slide is just to let you know that we are almost limitless about who we actually license and partner with. We have small businesses here that are located here in our region in Hampton, Virginia, all the way up to middle-sized and larger businesses like you see on the chart, namely Pepsi, for example. And so we have a lot of exciting opportunities, particularly for small businesses, and I'll talk about some of the opportunities that we have where startups can get some breaks in licensing our technologies. Since you're here with us today on the webinar, you're already somehow engaged with NASA Langley Research Center, and we're excited about that. But I wanted to make sure that you're aware of our technologygateway.nasa.gov website. It's a great and robust website that you can plug in keywords and you can find intellectual property having to do with those keywords and find out all the information that you might like to learn about our technologies here at NASA Langley. Generally, our intellectual property here at this center falls into the ones that you see listed here on this chart: advanced materials and coatings, aerospace applications, of course, like we've heard about today, sensors, detectors, and we have a large catalog of software. So please do visit our website. Now I'll talk a little bit about the types of licenses that we do offer. The first one I'll talk about is the commercial license. It is available to domestic and international organizations, and we can craft it so that it's exclusive, partially exclusive, or non-exclusive. So that is just based on your business plan. So if you have some type of field of use that you would like to carve out for exclusivity, we can certainly do that, and we can also enter into licenses that are non-exclusive. Each commercial license is negotiated on a case-by-case basis. They're not cookie cutter, and we pride ourselves here in our office, the Tech Transfer Office, very much in working closely with our licensees because we want you to be successful. I mentioned a few minutes ago about the startup license for startups, and the attractiveness of this type of license is that normally it's put in place for businesses that have been incorporated for less than 12 months, and there are no payments for the first 3 years. So you can actually get the technology in your hands to try it out, to see if it fits your needs. There are no upfront costs. They are only available to U.S. companies and only on a non-exclusive basis. But as I mentioned, the first 3 years there are no fees, and that's often very attractive for startups. Another type of license, besides the commercial and besides the startup, is what we have called the evaluation license. This is also a non-exclusive license, and it gives you the chance to evaluate the license for your needs. It's normally put in place for 1 to 2 years. It is also not exclusive. I believe I mentioned that. And it's one flat fee of $2,500. And for any of these types of licenses, I'm happy to answer questions at the end, should you type into the comment box. So where do you get started? You submit an application. Some of the things that are required for submitting an application is a certificate or proof of incorporation, a financial statement with a business and commercial plan, projected revenue and royalty, and a company balance sheet. Different types of licenses require different types of information, but generally this is what we'll need to see from you. The things that are negotiated are the upfront fees, annual minimums, royalty payments, and certainly the field of use and the geographic locations for manufacturing and product sales. So again, as you contact our office and begin to ask questions and perhaps submit an application, we're here to help you through these things step by step. So just very generally, this is a summary of what I've already mentioned. You would, it's the licensing process and review. You would certainly find the technology, hopefully the TASAR that you've seen today. You would contact our office, which will we will provide that information at the end. You will talk with our office. You'll have a chance to talk to either business specialists like myself regarding licensing. We can also have you speak with some of our technology portfolio managers so that you may ask more technical questions regarding the technology. You would submit the application, as I've mentioned. Our office reviews it and determines that you qualify. We begin the negotiation process, and our office would provide a draft license for you to review, of course. And each party enters into an agreement, and you have an actual signed license document at the end. So I believe at this point I'll turn it back over to my colleague, Sean Sullivan. Thank you so much for your time today.
All right, thank you, Jennifer. So again, we have received a lot of questions about David's presentation, and I really appreciate all those questions that you've submitted. If you have any more questions that you want to submit, continue to type them to that chat box. We've only got about 5 minutes left, and to respect everyone's time, we're going to end right at 3, so we'll only get to a couple of them, but we will absolutely follow up with you in any question that you ask in the chat box through email following the presentation today. So we'll get back to you sometime within the week. If you have any other questions after today's webinar, you can also contact either Jesse Midget, the Technology Portfolio Manager for this technology. You can see his contact information there. Or you can reach our entire office by contacting us at the LARC-DL email address that you see at the bottom. So now that we only have a couple more minutes left, I'm going to get to the first question. And this one's for you, David. Does this technology apply for oceanic airspace? If so, why was Alaska's oceanic flights excluded, or why were they excluded?
Very good questions. So, in our initial implementation, we focused on domestic airspace, primarily because of the way the pilots make their request air traffic control and the flexibility that domestic operations has. You've got the published waypoints. Basically scattered throughout the domestic U.S. and, the operations generally are not restricted to the track system like they are in the oceanic domain. There certainly are areas of oceanic operations that are not track-based, and this would be a great area for implementation. There might have to be some technology adaptations and maybe some procedural adaptations to support how reroutes are accomplished in the oceanic domain. But just, for, our area of where we're starting in the domestic U.S. And focusing on, with our partner, Alaska Airlines, on their domestic operations. But fundamentally, the software is flexible. It doesn't have to be restricted to name fixes. It can use just latitude, longitude coordinates, and Oceanic also provides a great opportunity to explore the use of this technology under data communications.
All right, great. Thank you very much. This next question is, I'm not sure who it would be for. I think it's probably for you, Jennifer. What exactly would you get with this if you signed a license?
When you sign a license, what it says is it gives you the ability to make, sell, or use what is actually in the patent or the patent application. So it gives you the right to use the intellectual property. We're lucky with this technology in that David has a lot of good information that he can also provide in the way of papers and that sort of thing. We also often have licensees work on a very limited case-by-case basis directly with the inventor or inventors to help address questions and problems along the way.
Can I maybe just augment that just a bit? Also want to point out that our intention is to licensees to be able to provide the source code of the TAP software, as well as the somewhat limited documentation that we have. This is again derived from a research project, so we have the documentation that we have, but that would come along with with the license as well.
Okay. I think we have time for just one more question. We're at 2:59. So David, this question's for you, I believe. So we saw the device being run on basically an Apple iPad. Will this also run on an Android platform?
Oh, well, let me address the type of software it is and what it can run on. The software is written in C++, and we've developed it so that it can compile and run in a Windows environment, a Linux environment, and the display part of the software could also run in an iOS environment. The iPad is a very popular electronic flight bag for airlines and for general aviation. So the whole TAP software does not run on the iPad. It would need to run the main portion of it would run on a Windows or a Linux box, but could be viewed through iOS. So it's fairly cross-platform.
Great. Well, unfortunately, everyone, that is all the time that we have for questions today. Again, if we did not get to your question during this Q&A session, then we will absolutely follow up with you by email within the next week. And again, if you have any additional questions, please feel free to submit them to the email addresses you see on the screen right now. I want to thank David, I want to thank Jennifer, and I want to thank all of you for attending today. We really appreciate it. And until the next webinar, have a good day.